Good day, everyone. I hope you are all doing well today. By the way, I am Raymart P. Samarita together with Kenneth Morales. And today we are here to present a very interesting topic, which is glacial environments, processes, deposits, and stratigraphic records. At first, it might sound a little new or unfamiliar, but don't worry. Through this presentation, we will explain it step by step in a way that is clear and easy to understand. Glaciers may look like just ice, but they play a big role in shaping the Earth and telling the story of our planet. That is why learning about glacial environments is both exciting and important. In this discussion, we will take you on a short journey starting with what glaciers are, moving to the processes they do, then the deposits they leave behind, and finally the records they keep in the Earth's layers. So, as we go along, we encourage you to listen carefully because this topic will not only give you knowledge about glaciers, but also a deeper appreciation of how nature works in powerful and surprising ways. Before we begin with the details of our topic, let me first explain to you the outline of our presentation. Think of this as our guide or roadmap, so it will show you the order of the topics that we are going to discuss, so you will know what to expect as we go along in this discussion. Our presentation has 9 main parts. First, we will begin with the introduction. Here we will answer two questions. The first one is why do we need to study glacial environments? And the next one is what is a glacial environment? This part will help us understand the importance of our topic. Second, we will talk about the environmental setting. So this part will explain the places and conditions where glaciers can be found. Third, we will focus on glacial ice and glaciers. We will describe how glaciers are formed, what types they have, and what makes them important in shaping the Earth's surface. Fourth, we will explain the glacial processes. These include erosion, transport, and deposition. In simple words, these are the actions of glaciers, how they wear away rocks, carry materials, and leave deposits behind. Fifth, we will explain the sub-environments and their deposits. This has 4 parts. The subglacial and ice marginal deposits like till and moraines, the glaciofluvial deposits such as outwash plains, eskers, and kames, glacioclusterine deposits which include verbs and dropstones, and marine glacial or glaciomarine, which include verbs and dropstones. Sixth is stratigraphic makeup. This part will show how glacial deposits are arranged in layers and how these layers tell us the story of Earth's past. Next is summary and characteristics of glacial deposits. And the last is the references. So that is the outline of our presentation. Through these topics, we will see how glaciers form and how they shape the land and why studying them is important.
Why we study glacial environment? Glaciers are powerful agents of landscape modification, acting as a system erosion, transportation, and deposition. Number two, they create a distinct sedimentary record that is crucial for interpreting past climate conditions. Lastly, glacial deposits are key indicators in the rock records for periods of major glaciation, and it provides the key of evidence of the past ice age and help professionals like us geologists understand Earth paleoclimate. Next, glacial environment. The glacial environment stands as one of the most powerful and dynamic sediment dispersal system on Earth, capable of sculpting an entire landscape and generating a vast of complex of soot sedimentary deposit. As comprehensively detailed in both Gary Nichols' Sedimentology and Stratigraphy and Sambog's Principle of Sedimentology and Stratigraphy. Glacier sedimentation is unique in its mechanics, its landforms, and the character of its sediments. It is an environment dominated by immense energy of moving ice, which acts as a primary erosional agent, as a transporter of unparalleled capacity, and a depositor of poorly sorted sediments. Okay, glacial environment are the region characterized by the presence of ice in the form of glaciers, ice sheets, or ice caps. As you can see here, we have figure 1 and 2. Um, one of the famous countries that has glacial environments are Chile, Canada, Russia, Greenland, and Argentina, and northern way when you can see a northern light. Next, we have environmental setting. The glacial environment proper is defined as all those areas in direct contact with glacial ice is divided into the following zones. One, we have subglacial zone, supraglacial zone, inglacial zone, ice contact zone. First one is subglacial zone. This is the area at the very base of the glacier, direct influenced by its contact with the underlying ground. It is where processes like erosion and the deposition of basalt occur. Subglacial zones are like canals underground. It is also responsible for glacial movement, erosion, and sediment transport. Next, we have supraglacial zones. This refers to the top surface of the glacier, which is exposed to the atmosphere. It is characterized by melting, debris accumulation, and the formation of the surface fissure. Superglacial zone is the surface. One of the primary of this is snowfall is the primary form of accumulation in the superglacial zone. This snow gradually compacts and transform into glacial ice, and it serves as climate indicator when we see an increased melting, and then it can be indicators of climate change. And next, we have end glacial zone. This is the internal interior of the glacier between the base and the surface. It contains transported debris within the ice and meltwater flowing through tunnels and fractures. In glacial zone, it also records climate change, like air bubbles trap within the in glacial zone ice and preserve samples of the vast atmosphere. It's providing us available data for climate recor- reconstructions. Lastly, we have ice contact zone. This is the area immediately around the margin of the glacier where ice directly influences near land and sediment. It includes features like meltwater channels and deposition that support by ice. Ice contact zone also importance of this can support ecological communities like plants and animals that specialize to adapt cold and watery environment. Next, we have distribution of glacial environments. Glaciers form in areas where annual accumulation of snow exceeds its loss through melting, evaporation, or wind. This requires a climate that either very snowy with mild summers or consistently cold. This condition can occur at any latitude, leading to two main types: temperate glaciers and polar ice caps. Temperate glaciers form at high altitude where winter snowfall exceeds summer melt. Snow compact into the ice in the high elevation, accumulation zone, and ablation zone, where melting occurs. A glacier archives a stable size when its forward flow is balanced by the equal rates of accumulation and melting. This equilibrium is distributed by the climate change. Cooling promotes glacial advance while warming causes glacial retreat. Even though the ice within the glacier never stops flowing downhill, although most temperate glaciers end on the land, those in a very wet, high precipitation region can flow rapidly all the way to the ocean where they lose ice through both melting and calving icebergs. To further explain, we have here a figure. On the top, glaciers grow when more snow falls in the winter than melts in the summer. If the top of this mountain fills up more snow than it can hold, the snow slides down. Mountain glaciers are like snow cones on a hill. Snow piles up at the high and then squishes into ice and slides down to where it's warmer and the ice melts. If the weather gets colder, the snow cone gets bigger and slides further downhill. If it gets warmer, the snow cones melt and get smaller, even though it's still sliding down a bit. Some of the snow cones are so big and the weather is so wet that they slide all the way to the ocean. Then big chunks break off and become icebergs. In contrast, polar glaciers exist in low precipitation regions where year-round cold temperature prevent melting. Here, ice accumulates into massive continent in spanning sheets and domes that bury the landscapes, with exposed rock peaks known as nuttocks. This ice flows all the way to the sea, where it feeds massive floating ice shelves. Due to its lower density, the ice floats. The edge of these shelves breaks off to form icebergs, which can drift for a vast distance before finally melting. Glacier ice, though solid, behave as a ductile materials under the pressure exerted by its own weight. Flowing like an extremely viscous fluid, this flow occurs at highly variable rates, ranging from a few meters to hundreds of meters per year. Movement is driven by pressure gradients and occur through internal deformation within the ice mass. The flow rate is typically fastest at the surface and slowest at the base. In valley glaciers, the flow is also fastest along the center line of the valley and decreases towards the margins where friction with the valley walls slow movements. In addition, uh, the flow is critical for glacial erosion, transportation, and deposition, shaping landscape over time. And in summary, glacier flows like slow honey and shaping the landscape as it moves. Now we're going to thermal regimes of glaciers. Based on their thermal regimes, glaciers are classified into three types with distinct behavior, particularly regarding movements and erosion. One, we have cold glaciers. Second one is polyglaciers. And lastly, temperate glaciers. First we have here is cold glaciers. These are the frozen to their bedrock substrate year-round. Movements occurs slowly through internal deformation, with upper layers searing over lower stationary ones. As there is no basal sliding, they cause very little motion and primarily transport debris that falls onto their surface from valley walls. In these cold glaciers, is that they are typically found extremely cold region with a little no meltwater at the base. Next, we have polythermal glaciers. These are the primarily cold base but experience periodic surges. Pressure from accumulating ice can melt the base, triggering a brief phase of rapid movements by a basalt sliding. During these surges, the glacier becomes a powerful agent of erosion. It subsequently freezes to the bedrock and returns to a state of internal deformation until the next cycle. These glaciers are sensitive to change in ice thickness and basalt temperatures, making them useful indicators of climate change. Lastly, we have temperate glaciers. Commonly in lower latitude, the ice is constantly at the pressure melting point throughout. This allows for continuous basalt sliding, making them highly effective and erosion through abrasion and blocking. They are the major source of sediment, generating everything from the fine rock floor to large boulders that are later transported by meltwater. Um, the type and size of glaciers are directly related to the local climate and topography, making them valuable indicators of environmental condition.
And now, let's move on to glaciers.
Glaciers in high mountain area, small cirque glaciers form in the protected hollows on the mountain slides and are found at high latitude all over the world, even within a few degrees of latitude from the equator. Major mountain ranges in moderate and high latitude also contains valley glaciers, body of ice that are confined within the valley slides. In the high latitude valley, glaciers may be fed by a larger body of ice at the higher latitude, which the ice caps that molly or partially blanket the higher parts of the mountains. The lower slope of the mountain's range may be the site of formation of a Piedmont glaciers, where valley glaciers may merge and spread out as a body of ice hundreds of meters thick. Next, erosional glacial features. The geomorphological evidence of the past glaciation, such as cirques, Yusuf valleys, and hanging valleys, is predominantly found in upland areas and geologically ephemeral as these features are eventually erode away. Smaller scales evidence like glacial stria on bedrock surface including roche monte and scratch marks on the clasts within glacial deposits provides more durable indicators. Discussed surface features are particularly important for identifying pre-quaternary glacial deposit in geological record. Um, while large landforms are impressive, these smaller features are crucial for identifying ancient glaciations in the rock record. Now, we are going to glacial processes, how sediment is handled. We have here erosion. Erosion have two parts, abrasion and quarrying blocking. First one is abrasion. Rock fragments dragged at the base of the ice create scratches and polish on bedrock. While quarrying, ice freezes into bedrock, tearing away blocks as it moves. To summarize this, glaciers act like sandpapers. Addition is that the effectiveness of these processes depend on the ice thickness, velocity, and the presence of meltwater. The more water at the base can actually increase erosion by facilitating abrasion and blocking. Now, we're going to move how sediments transport. Sediment is carried on the surface, within the ice, and at the base. These procedures are heterogeneous mixtures of all grades sizes from giant boulders to rock floor. To further explain this, continental glaciers move debris into main ways. First one, in the part of supraglacial, an angular debris from the valley slide rides on the surface unchanged. The second one is in the basal. Debris from abrasion and blocking at the base include fine rock floor. Polythermal glaciers have more basal debris due to freeze-thaw weathering. Next, as I mentioned earlier, continental glaciers transport debris through two primary mechanisms. One is supraglacial and basal. Supraglacial debris consisting of coarse angular material from a valley slides accumulates on the surface and it's carried without modification. In contrast, basal debris entertained by abrasion and blocking at the bed. It contains a wider range of grain sizes, including fine rock floor, and the abundance of this basal debris is greatest in polythermal glaciers, where freeze-thaw cycle weather the bedrock. During transportation, internal glaciers deformation and the merging of the ice streams can mix these debris types, with the basal material being further modified by abrasion and meltwater sorting, while supralogical detritus remains unchanged. To top this all, An internal deformation and merging ice stream mix these and modifying basal debris to abrasion and meltwater, while supralogical material stays the same. This mixing is modification creates the unique, unsorted nature of glacial tilt with both angular and rounded class.
Now that we've seen how glaciers pick up and carry sediment, we arrive at the final act, which is the deposition. This is how the glacier drops all that material, creating the landscapes we see in formerly glaciated areas today. There are four key processes to understand. First, lodgement. This happens under moving ice. As the glacier slides along, it literally plasters or spears sediment onto the bed beneath it. Second, melt out. This occurs when ice carrying debris, either within it or on its surface, becomes stagnant and melts it in place, slowly releasing the sediment it contains. Third, dumping. This is a more dramatic process than the ice margin, where sediment carried on the surface slides, slumps, and collapses as the ice supporting it melts away. And finally, reworking. This isn't a direct glacial process. Instead, meltwater streams sort, redistribute, and deposit the sediment beyond the ice margin, creating layered and sorted deposits that look very different from those dropped directly by the ice. And now let's focus on the depositions by continental glaciers. The first one is direct deposition by ice, which deposits till and moraines. The most characteristic glacial deposit is till or boulder clay. Till is an unsorted, non-stratified, or massive and often unconsolidated mixture of sediment ranging from clay to boulders. It is deposited directly by the glacier without the reworking action of meltwater. Both Nichols and Boggs emphasize the following processes for till deposition. And here are the three main types of till. The first one is melt-out till, formed by debris melting out of stagnant ice. The next one is lodgement till. It is formed by debris being plastered underneath moving ice, often showing a specific fabric. This process produces a deposit that generally preserves the original composition of the sediment in the ice. However, it can be easily disturbed and reworked as the supporting ice structure disappears. And the constant pressure and shear from the overriding ice make this deposit typically denser and more compact than other tills. Stones within it are often scratched and aligned to show the direction of the ice flow. Lastly, flow till. It is formed when glacial sediment is reworked by gravity flows. Flow till is not deposited directly by ice, but when previously deposited, glacial sediment becomes saturated with water and flows downhill like a slurry. This process creates a secondary deposit that can partially erase the original chaotic structure of the till. It often forms lobes or sheets on the slopes below a melting ice margin. And in addition, melt-out and lodgement tills are collectively known as basal tills. And so, as you can see in these diagrams, it helps us visualize these processes. You can see the different zones of debris, supraglacial on top, and glacial within the ice, and debris at the base. Lodgement till is shown being smeared onto the bedrock beneath the moving ice, and as the ice melts, the inglacial and supraglacial debris is released. Some of this debris forms melt-out till in place, and some of it may become flow till if it's reworked by slumping and flows. This figure perfectly shows how the different transport paths lead to different types of direct deposition. And now, let's move on to the moraines. When till is deposited in specific landforms, we call them moraines. These are ridges or piles of glacial debris. Moraines are accumulations of glacial till or debris formed directly at a glacier's margin. Several different types of moraine can be recognized. The first one is terminal or end moraine. It is a ridge that marks the glacier's maximum limit of advance and are typically ridges that lie across the valley. The next one is push moraine. It is formed when a glacier front bulldozes and piles up sediment from the valley floor. Unlike other moraines made from drop debris, this one is made of pre-existing material that has been thrust forward. Next one is dump moraine. It is formed at the snout when the rate of ice melting keeps pace with the glacier's advance. It essentially represents a steady state position where debris is constantly being deposited as the glacier moves. Next one is lateral moraine. It ridges of debris deposited along the sides of a valley when a glacier retreats. The debris is primarily rockfall from the valley walls that has accumulated on the ice surface. Next one is medial moraine, a line of debris down the center of a valley formed when two glaciers merge. They are a clear indicator of glacier convergence and can be seen snaking down the length of the glacier. And the last one is ice core or ablation moraine, a layer of debris that covers and insulates the ice beneath it. As the hidden ice core slowly melts, the moraine's surface becomes unstable and collapses into a hummocky or lumpy landscape. So in this figure, it shows how a glacier, like a giant conveyor belt, transports rocks, soil, and debris. As the glacier flows downhill, it picks up material from its sides and base. The piles and ridges of this deposited material are called moraines. Also, in this image labels the specific types of moraines based on their location on or around the glacier. The first one is lateral moraine. These are long ridges of till piled up along the sides of a glacier. They form from rocks and debris that fall from the valley walls onto the glacier's edges. Terminal moraine. This is a prominent ridge of till that marks the maximum advance or farthest downhill point of a glacier. It is deposited at the glacier's snout or end where the ice melts at the same rate it flows forward. It can act like a bulldoze pile of debris. And next is glacier flow. These arrows indicate the direction the glacier is moving from its accumulation zone where snow builds up to downhill to its ablation zone where it melts. Moraine in transit. This refers to debris that is currently being carried within the body of the glacier in glacial or along its base. It hasn't been deposited yet. Supraglacial moraine. This is the debris that is carried on the surface of the glacier. It often falls from the valley walls or emerges from within the ice as the surface melts. Medial moraine. This is a dark stripe of debris that runs along the center of a glacier surface. It forms when two glaciers flow together and their adjacent lateral moraines merge in the middle of the new larger glacier. Bed load. This is the material that is dragged, rolled, or slid along the very bottom or the bed of the glacier. This abrasive action is a primary cause of glacial erosion, carving out U-shaped valleys. In simple terms, think of the glacier as a slow-moving river of ice. As it moves, it scrapes up dirt and rocks from the ground and collects more rocks that fall from the mountain sides. The image shows where all this debris piles up. On the sides, lateral moraine. In the middle, where two glaciers meet, medial moraine. At the very end, where the glacier finally stops moving forward, or terminal moraine. So this diagram is a classic representation used in geology and geography to explain how glaciers shape the landscape through erosion and deposition. Now, let's move on to the deposition by meltwater or glaciofluvial deposits. It is a significant volume of glacial sediment is not deposited directly by ice but is transported and sorted by meltwater streams. These deposits are stratified, layered, and sorted, unlike till. Key glaciofluvial depositional environment include first one is eskers. It is a long, winding ridges of sand and gravel deposited by meltwater streams, flowing in tunnels within or beneath the glacier. As described by Nichols, they record a pattern of subglacial drainage networks. Next one is cames. It is a conical mounds or irregular ridges or stratified sand and gravel deposited by meltwater either on the glacier surface, in crevasses or moulin holes, or at the ice margin. When the ice melts away, the sediment collapses into a mound. Next one is outwash plains or sandur. Broad, flat plains of stratified sand and gravel deposited by braided meltwater streams, flowing away from the glacier front. Sediment on an outwash plain is typically well sorted, with grain size decreasing distally from the ice margin. And last one is kettle lakes. Depressions form when a block of buried glacial ice melts, causing the overlying sediments to collapse. These often fill with water and become sites for the deposition of the grain organic rich lacustrine sediments. In short, meltwater from glaciers doesn't just leave a messy pile of rocks. It sorts them by size and creates distinct landscapes like winding ridges, hills, flat plains, and lakes. This figure shows a landscape shaped by a past glacier. The main feature is a U-shaped glacial valley with debris piled along its sides as lateral moraines. The winding ridge of an esker marks the path of an ancient underground meltwater stream. Meanwhile, the cluster of a teardrop-shaped hills known as drum limbs indicates the direction of the glacier's flow. After the ice melted, mounds of sediment called cames were left behind, and meltwater streams deposited sediment to form the flat outwash plain or sandur. And now let's move on to the deposition in glacial lakes or glaciolacustrin deposits. Lakes adjacent to ice margins are major sediment traps. Their deposits are characterized by varbs, which are annual layers of sediment. As Boggs details, each varb couplet consists of first, a thick, light-colored layer of coarse, silt and fine and deposited in summer when meltwater inflows is high. Second one is a thin, dark layer of fine clay and organic material that settles out of suspension during the winter when the lake surface is frozen and inflow is minimal. And now let's move on to the last sub-environment, which is marine glacial environments or glacial-marine. Marine and glacial environments. Ice can enter marine environments in two main forms. The first one is ice shelves. It is formed when continental ice sheets extend over the ocean. They are floating, contain little sediment, mostly from the base, and act as a buffer to slow the flow of land ice into the sea. They break up to form icebergs. Number two, tidewater glaciers. It occurs when valley glaciers reach the sea. They can contain large amounts of debris from both their surface and base. A third type is sea ice is a simply frozen seawater and contains no sediment except for wind-blown dust. A key point is that melting floating ice, like ice shelves, does not raise sea levels, but their removal allows more land ice to flow into the ocean, which does cause sea levels to rise. Erosional features associated with marine glaciers. When continental ice from glaciers or ice sheets extends into shallow ocean areas, it can become grounded on the seafloor. This ice erodes the seabed in two primary ways: through glacial scouring, where the moving ice and icebergs gouge long, deep grooves into soft sediments, and through the action of high-pressure subglacial meltwater, which carves out channels known as tunnel valleys. These distinctive erosional features are often preserved within the sedimentary layers of continental shelves that were once covered by ice. In simple terms, when a massive glacier on land flows into a shallow sea, its bottom can hit the seafloor. As it keeps moving, it acts like a giant plow, scraping and carving the ground beneath it in two main ways. The first one is glacial scarring. The ice and trap rocks scrape long, deep grooves in the seabed. Second one is tunnel valleys. Meltwater flowing under tremendous pressure at the base of the ice carves out large channels. So these scratches and valleys get buried over time, but remain in the geological record, providing evidence of past ice ages. And finding these features on ancient seafloors helps scientists map where glaciers existed millions of years ago and understand past climate change. And now we move on to marine glacial deposits. So marine glacial deposits called till and tillite are formed from sediment released by glaciers into the ocean. They are categorized into two types. The first one is ice proximal deposits. It is formed near the ice front. These are poorly sorted and stratified dynamic tons. So because the sediments is dumped directly and rapidly by the ice with little water transport, these deposits are characteristically chaotic. They are classified as dynamic tons, meaning they are a completely uncertain mixture of sediment, sizes ranging from fine clay and silt to large boulders, all jumbled together without any visible layering or stratification. So the second one is ice distal deposits. It is formed farther away, primarily from sediment released by melting icebergs. These deposits are often reworked by waves and currents, becoming sorted and stratified, and can mix with other materials like bigenic. So in simple terms, ice distal deposits form much farther out to sea, created primarily from sediment that was trapped within or on the surface of icebergs, which have calved from the glacier. As these icebergs drift and melt away, they release their sediment load. So this material is then frequently reworked and sorted by ocean waves and currents, often becoming stratified into distinct layers and frequently mixing with other marine materials, such as the skeletons of tiny sea creatures or bigenic sediment. And a key feature of ice distal deposits is drop stones, larger stones and boulders that drop from melting icebergs into the fine-grained marine mud. These are important indicators of past ice ages and cold climates, though similar features can rarely be created by floating vegetation. So, for us to further understand the marine glacial deposits, we have here a figure. So this figure shows how material eroded by continent-sized ice sheet is transported and finally deposited on the seafloor. So I'll explain it step by step. The first one here is floating ice sheet or ice shelf. So this is the extension of the continental ice sheet that has flowed onto the ocean. It is still attached to the land-based ice but is floating on the water. So it acts like a massive conveyor belt carrying sediment trapped within the ice far out from the coast. And the second one is the continental margin. So this is the underwater edge of the continent, comprising the continental shelf and slope. It's the primary area where these glacial marine processes are occurring. The third one is still sheet. So this is a thick, unsorted, and unlayered deposit of sediment. It forms under the grounded part of the ice sheet as the ice grinds against the bedrock. So when the ice sheet advances directly over the seafloor, it plasters this mixture of clay, sand, pebbles, and boulders onto the bottom, creating a tail sheet. And the fourth one is the laminated mud. So as you can see here, these are fine-grained, horizontally layered sediments found further from the ice edge. The laminations are created by seasonal settling of fine silt and clay particles in the open water. So this particle come from glacier floor. So glacial floor is a rock dust produced by the glacier grinding against bedrock, which is carried out by meltwater and ocean currents. Currents transporting fine material from other areas. And the fifth one here is the icebergs. So these are chunks of ice that have broken off or calved from the front of the floating ice sheet. They carry rocks and sediments of all sizes that were trapped within the ice. And the sixth one is drop zones. So this is the most distinctive feature of glacial marine environments. So as icebergs float into warmer water, they melt. And when they melt, any rocks or large pebbles they are carrying are released. So these stones drop through the water column and land on the fine laminated mud on the seafloor. So when a dropstone lands, it disrupts the delicate layers of mud. Later, more mud is deposited on top, burying the stone. In a core sample taken from the seafloor, a geologist would see a lone pebble or boulder sitting in the middle of fine laminations that are bent downward beneath it. And this is definitive proof that the stone fell from above, indicating the past presence of icebergs. So that's all for the glacial marine or marine glacial environment. So let's now move on to the summary of glacial environments. So composition. Glacial deposits are compositionally immature. This means they are made of unweathered, broken up bedrock from beneath the glacier, lacking the sorting and refinement seen in other environments. Next, clay and weathering. There is a notable lack of claymate minerals because the cold climate inhibits the chemical weathering and processes needed to create them. Preservation and continental deposits, example tills on land, have a low preservation potential as they are easily eroded after the glacier retreats. Glacial marine deposits, sediments laid down in the ocean, are much more commonly preserved in the geological record. These include distinctive features like dropstones or stones dropped from melting icebergs, which serve as key evidence for past glaciation. And lastly, global importance. The growth and melting of continental ice sheets are directly linked to global sea level changes. Therefore, studying past glacial periods is crucial for understanding the history of Earth's climate. And now let's move on to the last part of our presentation, which is the characteristics of glacial deposits. So the first one is the lithologies. So lithologies is conglomerate, sandstone, and mudstone. So glacial deposits are made from the rock and sediment debris that a glacier erodes, transports, and then drops as it melts. This debris is completely unsorted, containing everything from giant boulders to fine clay. When this material becomes compacted and turns into rock, it forms a conglomerate and sandstone and a mudstone. These three rock types represent the full range of grain sizes found in the original glacial mixture. Next one is the mineralogy. It's a variable, compositionally immature. So, because glaciers scrape across vast areas of land, they pick up whatever rocks and minerals are in their path. They not selectively transport only durable minerals like rivers or waves do. As a result, the mineral mix is variable and compositionally immature. So this means the deposits contain a mix of chemically unstable minerals that easily weather along with stable minerals. There hasn't been enough natural processing to separate and break down the weaker minerals. Next one is the texture. Extremely poorly sorted in till to poorly sorted in fluvio-glacial phases. So sorting refers to the range of grain sizes in sediment. So till this is the material dumped directly by the ice. It is extremely poorly sorted the ice is because the ice carries all grain sizes together and drops them in a chaotic mix. So you find large boulders embedded in a matrix of sand and clay. And fluvial glacial phases, these are deposits from meltwater streams flowing the glacier. The water sorts the sediment to some degree, separating the larger grains from smaller ones. So, however, because the stream input is so chaotic, the sorting is still not good, resulting in poorly sorted deposits compared to typical river deposits. Next one is bed geometry. Bedding absent to indistinct in many continental deposits, glacial-marine deposits may be laminated. So bed geometry refers to the internal layering or bedding of the deposit. Continental deposits, example, till, deposited directly by ice. These layers are dumped chaotically. There is no consistent layering, so bedding is absent or indistinct. It looks like a massive homogeneous pile of debris. And glacial marine deposits. When glaciers calve icebergs into the ocean, the debris trapped in the ice settles to the seafloor. This can happen in quiet, seasonal layers, creating fine, parallel layers called laminae. Next one is the sedimentary structures, usually none in tills and cross-bedding in fluvio-glacial phases. So sedimentary structures like ripple marks from the action of water or wind. So tills is deposited by solid ice, so there is no water action to create structures. Therefore, they typically have no sedimentary structures. So in fluvio-glacial phases, these are deposited by flowing water, which can create structures like cross-bedding or inclined layers within a bed, which forms from migrating sand dunes on the stream bed. And the sixth one is a paleo-occurrence. So orientation of clasts can indicate ice flow direction. As glaciers move, they can grind and drag elongated pebbles and boulders along their base. So these clasts often become aligned with their long axis parallel to the direction of ice flow. By measuring the preferred orientation of these clasts in ancient glacial deposits, geologists can determine the paleoccurrent or the direction the ancient glacier was moving. Next is fossils, so normally absent in continental deposits but may be present in glacial marine phases. So, the harsh, abrasive environment under a continental ice sheet is not conducive to life or the preservation of fossils. Therefore, fossils are normally absent in tills. However, in glacial marine environments, marine organisms like microfossils can live in the water column. When they die, their shells can settle to the seafloor and be buried along with the glacial sediment, making fossils possible. So the next one is color. Variable, but deposits are not usually oxidized. So the color of the deposits depends on the source rocks, so it is variable. However, a key feature is that they are not usually oxidized or rusted. Oxidation requires exposure to air and water, but glacial deposits are often quickly buried under more ice or sediment in cold, waterlogged conditions, preventing the iron-bearing minerals from turning reddish-brown. And lastly, the phases associations may be associated with fluvial phases or with shallow marine deposits. So, phases associations are the other types of sedimentary environments found alongside glacial deposits. So, glaciers are not isolated, they interact with their surroundings. Therefore, glacial deposits are commonly found in associated with fluvial or river phases representing the meltwater streams that flow from the glacier associated with shallow marine deposits, representing where the glacier met the sea, an ice shelf or calving icebergs. And that's all for our presentation about glacial environments. Again, I am Raymart P. Samarita, together with Kenneth Morales. Thank you so much for your time listening to our presentation. Hanggang sa muli, paalam!